Hello everybody, I hope you're all doing well. We are going to be looking at the idea of frames today, and then we'll go on to a solved problem on the same. Alright, so frames. Frames are also used for structural support. In that sense, they are similar to trusses. Okay, so they are also used for structural support. And a typical example of this is a bicycle frame. Okay, so example is a bicycle frame. But there is one fundamental difference between a truss and a frame. Okay, so here is the difference. In a truss, all the bars of a truss are two force members, but that is not necessarily true of frames. It is possible that in frames you can have at least one bar that is not a two force member. Okay, so a fundamental difference between truss and a frame. Difference between truss and a frame. Okay, this is very important because we have to identify, okay, is this a problem on trusses or is this a problem on frames? Okay, so in trusses, we know that all the bars of a truss are two force members. But if I have a frame, that is not necessarily the case. Okay, so if I have a frame, not all bars of a frame are two force members. Okay, so this is the prime difference between the two, and the consequence of this, is that if I have a frame, then the external forces can actually act on the bars of a frame. Okay, so here one more thing that you can think of, and let me scoot these differences up a little higher so that I can add in a problem which I have already prepared for you. Okay, so if I look at a truss, the forces act only at the pins or the joints of a truss. Okay, so let me bring this down here. So if I look at a truss, the applied forces or external loads act only at the pins or the joints. Okay, but if I have a frame, that is not necessarily the case because of the fact that not all bars of the frame need to be two force members. I can have forces, external loads acting on the bars of the frames themselves. Okay, so the external loads can act directly on the bars of the frames. Okay, so these are the foundational differences, and this is what essentially allows us to distinguish between a frame and a truss. Okay, so the key difference is that if I have a truss, all the bars of a truss are two force members. Okay, if I have a frame, that is not the case. And since all the bars of a truss are two force members, the external loads act only at the pins or the joints. But if I have a frame, that is not necessarily the case. It is quite possible that one of the bars of a frame is a multi-member bar or a multi-member body. Okay, it's not a two-force body anymore, so that the external loads can act directly on the bars of a frame. Okay, and you can also have external loads acting at the pins or the joints in a frame, but there will always be one bar at least that is a multi-force member, which is not a two-force member. Okay. Alright, so this is a fundamental difference, and so now we come to a problem, and I have the problem prepared for you here, as I said. So here is a problem. And in the previous lectures, we've been looking at the concept of distributed loading. So this problem contains a distributed loading scenario, as you can see here. Okay. Alright. So what do I have? I have the bar AB, and then I have the bar BC. There is a pin support at A, there is a pin support at C. and the two bars are pinned together at pin B. Okay, so let me maybe write this down. So I have bar AB and bar BC are pinned together at the point B. Okay, that's the first thing. There is a distributed load acting on the bar BC. Okay, distributed, rectangular distributed load, as you can see. Distributed load acting on bar BC. Okay, so this is what we have here, and what are we supposed to find? Okay, we are supposed to obtain the reaction forces. Reaction forces at the pins A and C. Okay, then obtain the force exerted by bar AB on the pin at B. Okay, then one more thing we need to find out is obtain the force obtained, exerted by the bar BC on the pin at B. Okay, so these are the three things that we need to obtain. Okay, and here is the problem. And the key to this problem is to first of all identify, okay, the solution strategy, if you want to think of it that way. Identify whether this is a frame or a truss. Now, is this a truss? It is obviously not a truss because the force is acting directly on the bar BC. Okay, so this is a problem on frames. Frames typically will contain multiple members connected together. Okay, so that's another thing that you can think of as a frame. Maybe I'll write this down as well here. Okay, so they will contain multiple bars pinned together with forces acting on the bars and the pins. Okay, so they may contain multiple bodies pinned together or bars pinned together okay, and as you can see, the forces can act on the bars and the pins as well. Okay, or only at the bars or only at the pins. Alright, so we go back to the definition of a frame. They're used for structural support and they contain multiple bodies or bars that are pinned together, and the forces can act on the body of the frame itself, which is not the case in a truss. So if I come back to this problem here, I see immediately that the bar BC has a force acting on it. So this is a frame problem, not a truss problem. Okay, so solution strategy. Okay, so the first thing I do is identify whether this is a truss or not. Okay, so this is a frame and not a truss. This is because of the distributed load or the external load acting directly on the bar BC. Okay, so this is a reason why this is a frame. All right, and since this is a frame, I'm going to just bring our problem back onto the next page so that I can start working on the details of this problem. Okay, so that is the first thing I do is I see, okay, hey, what do you think this is? What does this look like? This looks like a frame. All right, the second thing I do is this: replace the distributed load by a single equivalent force. Okay, and we have seen the idea of a rectangular distributed load. So what I'm going to do is I'm going to take this problem that we have, and I'm going to say, okay, hey, this problem is now going to be replaced by the following problem. Okay, and here is what I'm going to be doing. I'm going to copy just the basic elements of this one without hopefully the distributed load and so on. I think I'm successful. Okay, and then I'll bring it down here. So I'm going to replace this by the following problem. Okay, so instead of the distributed load, which I'm going to show in a dotted line, in a set of dotted lines, okay, as you know. Okay, and let me complete this here. Okay, it's acting on the entire bar, so that's something that you want to keep a note on. It's not acting only at some portions of the bar or anything like that. Okay, so I'm just going to make these as dotted lines so that we know that, hey, there was a distributed load here, but I have replaced it by this single equivalent force. Okay, so I'm going to replace that by a single equivalent force. I'm going to call that force as F suffix R. It's going to be acting in the same direction as the intensity of the load distribution that you can see there. Okay, so that's something that you can also figure out by the way the force is acting. Okay, so this force I'm going to call as F suffix R. Okay, and then a couple of things about F suffix R. Okay, first thing is Fr acts in the same direction as the load intensity. Okay, which means that this force Fr is actually perpendicular to the bar BC. Okay, let me maybe draw that out in a much straighter line. Apologies. Okay, so this force is actually perpendicular to this bar. As you can see, the applied distributed load is also perpendicular to the bar. Okay, then I can also say that the magnitude of the force Fr is going to be equal to the area under the distributed load. Okay, so this is the area under the load distribution curve. Okay, so that the magnitude of Fr, I can write this as 100 times a distance of 5. So this is going to be 500 newtons. And in terms of units, if I were to be a little more careful, here is what I would have done. Okay, so I would have called this as 100 newtons per meter multiplied by 5 meters, so that Fr is obtained as 500. The meters and the meters cancel off, and then I'm ending up with a magnitude of 500 newtons. All right. Then what is the distance at which it acts? It has a line of action passing through the center of the load distribution curve, right? So that's the third thing that I can write. Fr has a line of action passing through the geometric center of the load distribution curve. Okay, and since that is the case, then we know the geometric center of a rectangle is right at its center. So I can say that, okay, hey, this is the geometric center of the rectangle. I'm not worried about how high away the force acts. I'm only worried about the length on the extent of the bar. So I can say the following. Okay, I can say that since this was 5 meters, the total length is now divided into two pieces, right? This is going to be 2.5 meters all the way from here to there, and 2.5 meters. Okay, so let me just make a slight mark here and say, okay, hey, this is going to be 2.5 meters from here to there. Okay, all right, so that's going to be aligned this way. So maybe I can do the following. I always kind of end up in a soup when I'm writing out these dimensions, but I hope you get the idea. Okay, I'm just going to put maybe a line here. Okay, that's supposed to be straight in a good way. All right, these little things get really tricky, I tell you. All right, so that's 2.5, and the extent of that is also 2.5, as you can see. Okay, so that's also 2.5. Okay, all the way up to there. All right. So with that said, we have now have everything done in terms of the load distribution. So I'm going to take this figure here. So these two are equivalent. So I'm reducing this to that one. Okay. So these two are equivalent figures. Okay. So reduce to that one. Okay. So I capture this figure here, which has been drawn with a lot of circumspection. All right. And then I'll bring this down here. Okay. And I don't like the look of all of these creatures, so I'm just gonna clean up my act and then call them, as you know by now, this is 2.5 meters and this is 2.5 meters as well. I think I should have done this the previous time itself. All right, now what do? I start by looking at the support reactions. Okay, look at this. There's a pin at A and then there's a pin at C connected to the ground, which means each of them are going to give me 4 support reactions. But if I look at the equations of equilibrium, I'm going to have only 3 equations of equilibrium, right? So what am I going to do? I can't solve for all the support reactions, so that is not a good move, okay? So here is what I say. So then look at support reactions. At A and C, okay? If I drew a free body diagram of the entire frame, okay, I would have 4 unknown reactions, 4 unknown reactions, right? 2 reactions at A and 2 pin reactions at C. So 2 pin reactions at A and 2 more at C. But I have only 3 equations of equilibrium. Okay, since that is the case, I cannot proceed forward. Okay, so which means that this is not a good move to draw the free body diagram of the entire frame. Okay, that is, if I draw the free body diagram of the entire frame, I cannot find all the unknowns. Okay, so that's what I'm trying to say. So if we draw the FBD of the entire frame, we cannot solve for all the unknowns. Okay, now the question comes, okay, is this an indeterminate system? Is it statically indeterminate? And the answer is no. Okay, because I can break this into different pieces and then I can check and see, okay, do I have enough equations to, or enough number of unknowns and equations where they match each other. If that is the case, then yes, this is not statically indeterminate. So that's what I'm going to be doing. So now I'm going to go back to my idea of breaking this completely apart. Okay, as I break this apart, I'm going to have a pin at B and then the bar AB and then the bar BC. Okay, so that's going to be my strategy. So I'm going to take this guy, I'm going to bring it to the next page and I'm going to break this apart. Okay, so what I'm going to do is, let us dismantle or break apart the frame. Alright, if I break apart the frame, then I'm going to have the bar AB, the bar BC, and the pin at B, and then support reactions at A and C, okay, which correspond to those pins. And that's precisely what I'm going to be drawing. Okay, so I'm going to first take this bar AB, I'm going to copy that and draw that here. Okay, so that's the bar AB. Then I'm going to have the pin at B. Okay, that's one thing that I'm going to be doing. Of course, I'm going to have the pin at A as well. I'm not drawing the pin at A. Okay, then I'm going to have this bar here, Okay, so I'm going to copy that, and I'm going to bring that down here. I know that this FR has been taken care of, and let me get rid of all of these things, because I know now, and you know now, that these distances are 2.5 meters. Okay, I need to take care of that. Hang on a minute. Alright, it's getting more and more sticky. Alright, beautiful. Okay, so I'm done with that. So this is how I dismantle it, and if you want, you can also call the pin at A and so on, but it's not necessary because I'm going to directly draw the support reaction on the bar AB. Okay, so maybe if you want, you can take the pin and then draw it at this point here, okay, and draw it at this point here as well, so that the support reaction can be directly drawn on these bars themselves. So this is the bar AB, so here is A, this is B, then I have the pin at B, and then I have the bar BC here. Okay, all right, so this is the situation. After you dismantle, this is what you end up getting. Okay, then here is what I'm going to be doing. I'm going to be drawing each of the forces and so on. Okay, on the bar AB, I'm going to be drawing the support reactions AY and AX in the following manner. So this is AY, arbitrarily chosen directions, albeit with some thought. Okay, it's not completely arbitrary. And then I have the force CY, which is acting in the following manner, and then I have the force Cx, which is acting horizontally, chosen this way. Okay, then what else will I have? I'll have a pin at the point B, right, which means that I'm going to have pin reactions at B on the bar AB. I'm going to call them as the following. I'm going to call them as BY and BX. This is BY, and then I'm going to have BX. Okay, now importantly, we know from Newton's law of action and reaction that every body will exert a force of action on the other body it's in contact with, which means that there will be a force of reaction on the body that is in contact with the other body. So Bx and By is the force exerted by the pin at B on the bar AB. So I'm going to have an equal and opposite set of forces acting on the pin, which I'm going to call as Bx and By as well. But they'll be in the equal and opposite directions to what I have drawn on the bar AB at the point B. So this is going to be Bx, and I'm going to write all these things down, and this is going to be By. Okay, so this is what I'm going to be having. This is the pin at B. Then I come to the bar AB or bar BC. Okay, so when I come to the bar BC, I'm going to have a similar scenario as I have on the bar AB. Okay, I'm going to have the pin forces at C has been taken care of. Now I'm going to have pin reactions here. Okay, the thing here is, okay, do I know the direction of the pin reaction? I don't. Do I know what the pin reaction is? I don't either. So I'm going to call this as Bx prime and By prime. Okay, because I don't know whether this Bx prime and By prime is the same as Bx and By. Okay, so I just want to put a very quick note here before I want to show that there's an equal and opposite set here as well. Okay, so this is going to be Bx prime, and then I'm going to have a By prime. Okay, so note this. Here I call them as Bx prime and By prime to differentiate these from Bx and By on the bar AB, and the reason for that is because reason being, when I start the problem, I don't know if they're the same. When I start the problem, I am not sure if they are the same as Bx and By. Okay, I hope this makes sense to everybody. So what I'm saying is there is a pin at the point B, which means I'm going to have pin reactions. There are going to be X and Y reactions. Now when I start the problem, I don't know if they're the same. So why should I take any chances, right? So I just call them by a different name. All right. So now I'm going to bring each of these bars and then I'm going to write down what are all these forces on the bars. Okay. So let's do that one by one. Okay. So I'm going to bring the bar AB. So on the bar AB, what are the forces? Okay. So pin reactions at A. Okay. So these are your regular AX and AY. Then at the point B, I'm going to have the forces BX and BY. This is the force exerted by the pin at B on the bar AB. Okay. But what do you know? Something really nice is happening here, right? Because there are only two forces on the bar AB, this bar AB is actually a two-force member. Okay, that's something that you want to note. Okay, forces at only 2 points, I'm sorry. So since there are forces at only 2 points on the bar AB, this is now a two-force member. So it is possible for a frame to have a two-force member, but what we say is not all the bars are two-force members, okay? So since it's a two-force member, you can do the following. You can say, okay, hey, instead of drawing this BX and BY, I can just draw this as a single force, FAB. This is going to be along the line joining the points A and B, as you know very well by now. Okay, so this is a two-force member, FAB, and I'm going to have the same slope triangle as before. Okay, so I can say that FAB, the slope triangle is 3, 4, and 5 for this. Right, so this is 4, 3, and then 5. So I can say from looking at the bar AB that AX is equal to BX is equal to 3/5. I think I flipped my A, BY and BX, so let me, I just caught that mistake here. It's okay, you can call them anything you want, right, essentially, but let's just be proper. Okay, so it's BX and BY, and I think I was okay on there. All right, this is one more thing I need to, yeah, sometimes I'm a big doofus. So this is going to be BY and BX. All right, so I come back here. AX and BX is 3/5 FAB, and AY is equal to BY is equal to 4/5 FAB. Okay, so that's essentially what I wanted to show here, but this is only for the bar AB. Okay, these are the forces. Now let me look at the bar BC. Okay, what are the forces on the bar BC? I'm going to bring back its free body diagram, and once again, very quick recap. Look at the bar AB, force at the point A, force at the point B, forces at only 2 points on the body. Okay, that's why this is called as a two-force member. Okay, and because it's a two-force member, I can just draw a force along the line joining the 2 points, as you've been doing in your homework and so on. Okay, then I come to the bar BC, I grab that fellow. Okay, so that's this entire creature here. So I copy that, and then I bring that down here. So as I look at the bar BC, what are the forces acting on it? Okay, so there's a force CX and CY are the pin reactions at C. Now this BX prime and BY prime, these are the forces, as you know, these are the forces exerted by the pin at B on the bar BC. And then thirdly, I have this force FR is the external load. Okay, FR has a magnitude of 500 newtons, as you know from before. Okay, so this is not a two-force member now. BC is not a two-force member. since we have forces at more than 2 points on the body. On BC. Okay, so which is why I'm saying that this is a frame, because there is a force acting on a point which is besides the point B and the point C. Okay, so this does not let us make some simplifications, unfortunately, but let's move on. Okay, so these are the forces. At the point C, I have Cx and Cy. These are your regular pin reactions. At the point B, I have Bx prime and By prime, which is the force exerted by the pin at B on the bar BC. And then I have this equivalent force of 500 newtons, which is acting due to the distributed load that was acting on the bar. That's an external force. Okay, forces at more than 2 points. Okay, that's why this is not a two-force member anymore. Okay, so since we have forces at more than 2 points on the bar BC, at the point B, point C, and then some point in the middle. Okay, all right. Then I grab the last figure that I have, which is the spin guy, and let's see what's going on here. Okay, so I'm going to copy that, and I'm going to bring that down here. Okay, so on the pin, I see two sets of forces. Okay, so this force Bx and By is now the force exerted. This is a reaction force. Okay, let me call that way. This is the reaction force exerted by the bar AB on the pin at B, and then the force Bx prime and By prime, these are the reaction forces exerted by the bar BC on pin B. Okay, I hope this makes sense to everybody. So there are two sets of forces here, Bx prime and By prime, Bx and By. Bx and By is a reaction force exerted by the bar AB on the pin at B. Bx prime, By prime is reaction force exerted by the bar BC on the pin at B. Okay, and we also have to say that the force at point B on AB is equal and opposite to the force on the pin B due to AB. Okay, so that's something that you want to make a note of. So the force at point B on AB is equal and opposite to force at B due to AB, and vice versa for the other one as well. So let me maybe just copy this down and then just change some of these words down here. So maybe let me have both of them down on this page here. Okay, so that we start on a fresh lease of life, and I just change this to the bar BC because that's also the same thing. They're all forces of action and reaction, right? So this is force at point B on the bar BC should be equal and opposite to force at point B due to the bar BC. Okay, so these are the forces of action and reaction. Okay, so action and reaction. Action is equal and opposite to reaction. This is essentially Newton's third law that is applied here. All right, this is fantastic. Then the next idea, okay, well, this is not helping us solve the problem anyways. I'm just visualizing these quantitatively, qualitatively, so what's the big deal, right? But here is the idea. Because I have broken down each of these into smaller parts, I can say that each of them are in a state of static equilibrium. Okay, so I can say the key idea here is that each part of the frame is in static equilibrium. Okay, which means that I can apply the equations of static equilibrium for each of them. Okay, and which one do I start off with? I can start off with any of them. Okay, so let me start off with the pin at B. Okay, so which means that start with the pin at B. Okay, so I'm just going to grab my free body diagram from here. And of course we are neglecting the length of the pin. I just want to make a statement of that note here. So here note that we are neglecting dimension of the pin and treat the pin as a particle, like what we did for trusses. Okay, that's the same idea here as well, but let me grab my figure and then bring it down here. So I'm going to start with the pin. Hopefully I have the pin right. Fantastic. So this is the pin at B. If I sum forces up in the horizontal and vertical directions, as you know, okay, forces in the x direction, this is positive x, and I say, okay, what do I get? Bx minus bx prime is equal to 0, which tells me that bx is actually equal to bx prime. Well, surprise, surprise. Okay, then if I sum forces in the y direction and set them equal to 0, what are the forces in the y direction? By minus by prime is equal to 0, which tells me that by is equal to by prime. So this is beautiful stuff. Okay, so here we come to a nice conclusion. Okay, so we come to an important conclusion. Okay, the important conclusion is the following. If, and let me go back, so keep these in mind. Bx is equal to bx prime, by is equal to by prime. Keep those in mind. Let me go back to my figure, my actual figure here. Okay, look at this. If there are only two bars connected together at a pin B, for example, in this case, and if there are no external forces or other forces, reaction forces acting at that pin, it's a, for example, this is a free pin, right? This is what we've been calling this as. So this is a free pin. Okay, so if two bars are connected together at a free pin, then the forces of the pin on those two bars will be equal and opposite on each other. That is what I'm saying, is that if there are only two bars connected together, then this force bx is the same as bx prime, by is the same as by prime, which means that these forces will be equal and opposite to each other. Okay, which means that if that is the case, then I don't need to draw the pin diagram, because I can directly visually see and say, okay, hey, I don't need the pin diagram. There are only two bars connected at that free pin. Okay, so this is one thing that I want to write down very carefully, and let's draw that here. So if at a free pin, meaning that means no external forces and no support reactions at that pin. So if at a free pin we have two bars of a frame, only two, okay, of a frame connected together, then at that point the force of the pin, then the force of the pin at the point of connection, okay, at the point of connection on the bars, will be equal and opposite on the bars. So for example, in our problem, B is a free pin, okay, and there are only two bars, connected at the pin B, which is the bar AB and the bar BC. Okay, and if this is the case, the force of pin B on bar AB, which is BX and BY, will be equal and opposite to force Bx prime and By prime, which is the force of the bar B on pin BC, which is the force of pin B on the bar BC. Okay, so this is an important conclusion, and if this is the case, then this will be used directly if we encounter such a situation. We don't need to draw the pin free body diagram. Okay, so in the future problems, so which means in future problems, future problem on frames, okay, if we encounter a situation as above, we do not need to draw the pin diagram, but instead we can directly say that the force of the pins are equal and opposite, okay, on the two bars. Okay, we can directly make our own conclusions. Okay, so we can directly say, we can then directly conclude that the forces on the bars are equal and opposite at the pinned point. At the pinned point are equal and opposite to each other. Alright, so this is a lot of writing. I just want to summarize this very briefly, and then we'll go on and wrap up this problem. Okay, it's not a big deal to wrap up this problem because we're almost done with pretty much everything we need to do. Okay, so here is what I'm going to say. We went and looked at each of these bars. Okay, we looked at the bar AB. There are only two forces on it, so this is a two-force member. Bar BC, there are forces at more than 3 points. So that's not a two-force member as such. It's a three-force member actually. It's not a two-force member. Okay, so this was forces at only 2 points, so that was a two-force member. Forces at more than 2 points, not a two-force member. So this is the frame. Then I went to the pin at B. There are sets of forces from 2 bars which are connected together at that pin. Based on equilibrium, I can show that these two forces are equal and opposite to each other. So we come to an important conclusion. If at a free pin meaning no external forces and no support reactions at that pin, we have only 2 bars of a frame connected together at such a free pin, then the force of the pin at the point of connection on the bars will be equal and opposite. And this is exactly what we have in our problem. At the pin B, I have the bar AB, I have the bar BC. They are connected together. At the point of connection, there are no external forces, there are no support reactions on the pin at B, which means that the force on the bar AB and the force on the bar BC at the point B will be equal and opposite. Beautiful. Which means now, and in the future, if I come across the situation, I'm not going to draw the pin diagram again. Okay, that's what I'm saying. So in future problems on frames, if we encounter such a situation as above, we do not need to draw the pin diagram. Okay, I will just directly see and mark it on the bars themselves. Okay, so now I come back and then I look at all these bars put together. Okay, so I'm going to bring the bar AB and the bar BC. Let me grab, okay, this is not my grabber tool. Alright, so I'm going to bring both of these together onto the last page here. And we're almost done. Okay, alright, well, who's counting, isn't it? Okay, so here is what I have. and I automatically can see that, okay, hey, these two are the same. First of all, we made a conclusion that by was 4/5 FAB, and then BX was 3/5 FAB, and then I also know that AY is the same as BY and AX is the same as BX. But then I also came up with a conclusion that BX prime is the same as BX and BY prime is the same as BY. So I don't need to mark them as two different sets of forces. Okay, so I can directly say, instead of BX prime and BY prime, I can just call them as BX and BY. There is no harm done. Okay, and then I start analyzing these things as rigid bodies. I already taken care of bar AB. AB is not going to give me any new information. Okay, because I already know that there is this force FAB, which you see here, which is acting on this bar, equal and opposite at both the ends of the bar. That doesn't look opposite. Okay, hopefully this is good enough. Okay, so this is going to be equal and opposite, so that's FAB as well. And you can write these in terms of FAB or BX and BY, it's your choice. Okay, so then I'm going to look at this free body diagram now. I'm going to look at this more carefully so as to analyze this bar. Okay, I'm just going to take this and redraw it a little bit. Okay, instead of BX prime, BY prime and all these kinds of primes, get rid of all of those creatures completely, because we have just proved that they're the same as BX and BY. I can now call this as 3/5 FAB and then 4/5 FAB. Okay, and then this force of FR, I can draw it in the following manner. You can check this and see. I can draw the slope triangle as follows. Okay, so if I look at its components, right, these are the components of the force FR, which will be acting, okay, one vertical and one horizontal component. They will be acting at the point of application, as you know. Okay, so please do not draw them in middle thin air. Okay, they have to actually act at the point of application. I can look at the slope triangle for FR. It's just going to be the inverse of whatever I have on this bar here, because of the fact that it's at 90 degrees. Okay, so let me grab this guy, bring that here. FR was well, why did that move back? Seems like a pretty, so that's 500 newtons. Okay, let me move this further away from the action there. Okay, and then I have the slope triangle of 3, 4 and 5, which is now going to be flipped as 4, 3 and 5. Okay, so this is going to be 3, this is going to be 4, and then that's going to be 5. Okay, because of the same slope triangle on right down here. So this is going to be in that case 400 newtons, and this is going to be 300 newtons. Okay, so this is what I've done. I have simplified it. Okay, so simplified, analyze the bar BC. The bar AB has been taken care of, which is how I was able to obtain 3/5 FAB and 4/5 FAB. Okay, so that's what I have done here too. And now I can just focus on this particular piece. Okay, so I'm going to grab just this particular piece and then move on with my life. Okay, then I can use the tools of rigid body equilibrium in order to understand that. Okay, so I'm looking only at this particular piece now, and I can start off by summing moments about C. Okay, so I have my coordinate frame X, Y and Z, and the Z comes out of the page, which signifies the rotation. So this is positive X, positive Y, and then this creature here counterclockwise. I sum moments about C. This is now your regular rigid body equilibrium problem, you see. Okay, if I sum moments, here is what I'm going to be ending up with. I'm going to have FAB, 3/5 FAB clockwise, produces a distance. So let me mark the distances. Let's do that. I think that might be useful. So all the way from here on to here, that's going to be a distance of 3 meters. Okay, and then all the way from the top here on to the bottom here, okay, that's going to be a height of 4 meters. Okay, that's 4 meters, and let me make these as dotted lines. As you know a lot of things about me by now. Okay, And let's grab this. Okay, fantastic. We got it all done. So this is now 3/5 FAB times the distance of 4 meters. So minus 3/5 FAB times 4. And then 4/5 FAB times the distance of 3. This is also clockwise. Times the distance of 3, that is also clockwise. And then you can do a quick trick. You can either take the 400 Newton force and then break it into a height here and then a 300 into a height. But I can take FR, which is perpendicular. You see the line of action of FR is perpendicular to this bar here, okay? So that's a perpendicular bar there, perpendicular line there, which means I can directly do FR times 2.5. That's going to be counterclockwise. That's equal to 0. Solve for FAB. That can be found out as 521 newtons approximately. Okay, so we have found out FAB. So that's beautiful. Once I find FAB, then CX and CY can be found out. Sum of forces in X direction is equal to 0. That tells me minus CX plus 3/5 FAB minus 400 is equal to 0. So I end up getting CX to be minus 87.5 newtons. Okay, so that's the value of CX for me. Let me just underline this here. Okay, and then I'm going to have the other one, which is the sum of forces in the Y direction. Let me just keep this figure down here. So this is going to be sum of forces in the Y direction. That's equal to 0. What do I do there? This is just a regular rigid body equilibrium problem, right? There is nothing more funner than that. Okay, so this is 4/5 FAB minus 300, which implies that CY is going to be the following value, minus 116.7 newtons. All right, so we're almost done then. Okay, so, and we already knew from before, if I go back and then look at my previous figures, I already know that AX was equal to BX, and that was 3/5 FAB, and this was the same as BX prime, right, as you know. And so all of these put together is 312.5 newtons because I know FAB. Okay, and then the other one is AY is equal to BY, which is equal to 4/5 FAB, which is also the same as BY prime. Okay, this one put together will be around 416.7 newtons. Okay, because I know FAB as 521 newtons approximately. And then the third one was CX was minus 87.5 newtons, and then CY was 116.7 newtons. Okay, so this was the summary. Okay, very brief summary of what we have done. Okay, so AB is a two-force member. Okay, the pin reactions or support reactions at A are AX and AY, which we just calculated as 312.5 and then 416.7 newtons. Okay, so that's one thing. Then the second thing is BC is not a two-force member. Okay, and we had support reactions at C. These were CX, which was minus 87.5 newtons, and CY, which was 116.7 newtons. And let me just scoot this up a little bit, all of these put together, so that I have some space to complete everything down here. Okay, and then the force exerted by the pin at B on the bar AB. Okay, this is going to be BX and then BY. Okay, which was 3/5 FAB and 4/5 FAB. We found this as 312.5 newtons, and this was 416.7 newtons. And I'm seeing if I can squeeze some of these things up here. Let me see. I could probably do that. Hang on. I'm just being a little stingy with space. I'm not sure why I'm doing that, but stranger things have happened. All right. So then the last one is the force exerted by the pin B on the bar BC, which is Bx prime, which is the same as Bx, and By prime, which is the same as By. Okay, so this is something that we already have written on the top here. Okay, and so this is the summary of the problem, and very, very quickly I just want to go back to our problem and then look at it from the beginning. Okay, so first of all, I had this problem here with the distributed load. This is not a truss, this is a frame, because the force is acting on the body of the bar BC. So that's the first thing. That's great news. Makes my life more miserable, right? All right. Then what do? Okay, I get rid of the distributed load by replacing it by single equivalent force. Fantastic. Okay. Then what do after this? I don't know what to do because I can't draw the free body diagram of the entire frame. It is not a useful exercise because I then am stuck with 4 unknowns, 2 at A and 2 at C. I have only 3 equations of equilibrium, so I cannot find all my unknown quantities completely. Okay, so which means that I just break them apart in the following manner. Once I break them apart, I say, okay, hey, each of them are individually in static equilibrium. So I look at the pin at B and I figure out these two forces are equal and opposite, and then we come to the conclusion that if I have a free pin, then and if there are only two bars acting at that pin or connected at that pin, then I don't need to draw the pin free body diagram anymore. I can directly say that the forces on these 2 bars are equal and opposite. And using that particular idea, I come down here and I see, okay, hey, this is great news. I'm just going to do the exact same thing on my bar here, which is bar A, B, and BC. Combine all the forces together. Look at the bar BC. This is now just rigid body equilibrium in 2 dimensions. Find out the unknowns and then call it a day. And here is the summary of what we have done. All right. Appreciate your patience. This is an important class or an important lesson. If you understand this, then frames will be very, very simple. Okay, it will just be an exercise in solving rigid body equilibrium problems again and again. That's about it. All right, all of you stay safe and take care of yourselves. Bye-bye.